It's like feeling the person time linear direction.
Sorry. Okay, we should start. So what we're gonna focus on today is building on what we've been discussing last time on how to build a model in Stan. We will be enriching our model in order to have a good workflow that ensures that our models are working the way we think they're working. But the plan is that first, I want to take a few minutes if you have outstanding questions and comments, in particular about the general tempo and level of the course, and whether you're finding the different resources useful or whether there's some issues. Right? And by the way, I linked the slide just a few minutes ago in the right space. So how is the level and tempo? I can go faster, I can go slower, but
maybe not faster.
Yes. Okay, good. Yes.
I think sometimes it's a little bit complicated.
Yes.
Sometimes you take a bit of detour and it's a bit hard to figure out whether you really need to understand this or whether it's just like a fun fact.
Well, it gets complicated. It's an advanced cognitive modeling, but it's a fair enough point. So you always very welcome to raise your hand and say, how important what is these detour important for, right? Is this going to help us code or think better models, or is it more like background understanding of what goes on under the hood, right? So for instance, I was just rechecking the questions on the Google Doc, and there's somebody who asks about the target plus equal notation, and understanding what that is about is not necessary to build a good model, right? It's just as you're writing these code, right, you want to know what that is about. Why is it that way? And that part is, in a sense, important for your deeper understanding of what goes on, but it's not important for your being able to think cognitive models, implement cognitive models, stress test cognitive models, and deploy them. So in that sense, you're always welcome to raise your hand and say, what do we need these for? Good. Are you worried about, because if you look at the timeline in the slides, we're sort of taking the time it takes to go through the different topics. So we're slightly delayed compared to that. I really don't care because I really want you to understand the different things. Is that something that bothers you? Good. How are the resources, right? So you have the slides whenever I remember to link them. You have the Q&A, and you have the possibility of watching the videos, and you have the course note, which I fully agree, they're not a finished product. They're just something you can use as a additional resource. But do you have comments on that? Is there something that, yes?
So I really like the course notes. I think it's a very nice sum up of what you've been talking about. Or like during portfolios, we've been using them a lot. Like,
yeah, that's the idea, right? That is, sometimes I don't have time to go through all the code or to unfold the full thing. And in the course note, there's the whole background coding that I've done to prepare the lecture.
Then I like the way that you framed meetings. Like it fits very well with how I understand things best. That you do the lecture first, and then if something is really confusing, then I go back and look at like the target thing.
Cool. So this is working. More attention to detours, framing them right, and being explicit. Any other comment on?
This is about resources, it's about assignment feedback.
Yes.
It was just that I know some of the groups had turned them in early and got like quite extensive feedback, it seems like, and then we were a group that turned it in on the day and we got minimal feedback and you didn't have a chance to look at our code. So it was just more, should we be trying to turn them in beforehand if you obviously have more time, or it was just,
So the general policy for feedback is collective feedback, because I cannot assure that I have time to look at the individual parts. Sometimes I have time, and therefore I put more into that, but the part, yeah, so if you submit earlier, it depends. Like some weeks I might have more time, some weeks I might not. But I try to ensure that there is a general, these are the important points that I give as a feedback to everybody. I think that in that case, what also happened is that I pointed to 2 or 3 key points that had emerged from the assignments that I already looked at in the class. And therefore, if the same comments would be repeated in the evaluate or in the feedback to the individual assignments, they were not repeated because they were the same as what was publicly given. But I'll try to keep an eye to make it a bit more even. Yes, I think that's a fair point.
also because the groups that have sent it in early are probably doing well.
Yes.
So it was just that they
Yeah.
were struggling and taking more time and getting less.
Yep.
It just, yeah.
Cool. Anything else? Good. So what we're going to do is Bayesian workflows to assess model quality. Now you've learned how you code your model with data, with the parameters and the model blocks in Stan. And the idea is that now we want to cover principled modeling practices, which in a sense overtake and integrate a lot of the stuff that you were supposed to have done in previous courses, like assumption checks for your models, residual checks, power analysis, blah, blah, blah. So we're all gonna drop all that long list of things that we might be supposed to do and integrate within a principled way of thinking about your model, all the checks that you need. And I know some people have questions about power, and we'll see how that works within this framework. In particular, we're gonna be looking at checking priors and the consequences of priors, checking how the fitting went, and checking parameter recovery, which is a more general principle that takes over what was done in power analysis. So what is a workflow? A workflow is a sequence of processes through which a piece of work, here a model or an analysis, passes from initiation to completion. It's something that's very discussed and researched in industrial organization because it gives us a framework to do better work without having to follow a long series of ad hoc rules. It's just a structured way of working. Here it is a scaffold that ensures that your model and analysis can do what you think it does. What are its limits and cautions to take when making an inference, etc. Right? It's a good set of practices to stress test what you're doing, right? Seeing where it breaks, because it's going to break somewhere, and you want to know where it breaks. One of the readings that I put, 10 rules for computational modeling or something like that. This is the kind of diagram that summarizes the workflow they suggest. You design an experiment and build models in interaction with each other. You simulate model and experiment. You do parameter recovery, which we cover today, model recovery, which we cover next week or the week after. Can the model and the experiment answer question in theory, right? Even when you simulate data from the very same model where you know the truth, can the model reconstruct it, or at which condition can the model reconstruct it? If not, you go back. If yes, you fit it to real data, you check the parameter fits, you do model comparison, you validate the model, and then you have the big question, has this worked on empirical data? Has that improved your understanding of the empirical data? And is it describing it in any meaningful way? No, you go back. Otherwise, you can report your results and blah. Another kind of workflow is the one in the paper on the Bayesian workflow, which has been a labor of love of a lot of the STEM developers, as you can see from all the million different points, right? You pick an initial model, you do prior predictive checks. You can see whether what the predictions from the priors are fit what you know of the domain, the phenomenon of work or not, right? If they contradict, you have a bunch of ways of modifying the models, and then you go back. If the prior seems okay, you fit the model, you do a lot of diagnostic. If this is not valid, you address this issue. If it's valid, you go back and you evaluate and use the model, blah, blah, blah. In particular, what I really appreciate of these diagram is something that is missing from a lot of the diagrams. Sometimes your models are just crap. And that's okay. We learn something from trying to build it. So what we're going to do is to go through a streamlined version of these kind of workflows. Right? Oh yeah, actually, I haven't read it, but just last weekend, there was a new paper that presents a Bayesian workflow, very similar to the ones that are discussed there. There's somebody we know here, Chris Mattis, and it presents this kind of workflow for the hierarchical Gaussian filter. But I haven't read it, so I can't tell you how it relates to the other. Okay, so how do we go concretely at implementing these kind of workflows, right? So before we feed the data, we want to deal with the choice of priors and the prior predictions, where priors pertain to the parameter level. So if we think about reinforcement learning, right, we have a learning rate, which goes from 0 to 1, which kind of prior we put onto that. The prior predictions pertains to the observed behavior, to the outcome. That is, in the matching pennies example that we've been dealing with, how many times will the participants or the simulated participant choose left and right, but also how will the simulated participant react to a certain sequence of stimuli, right? We can also split it and say, well, what if they just won and the opponent played left? Out of 1,000 times, how many times is the simulated agent going to pick left or right, right? We want to visualize our priors, right? And why do we visualize our prior? Again, we discussed this a bit, both in lecture and class, but I'm just going to put it on the slides so it's very clear. We discussed defining priors for parameters like theta or learning rate that go from 0 to 1 on a log-out scale, right? Because the log-out scale magically shrinks whatever we put into that into a 0 to 1 scale when we do the inverse logic, right? And respects the boundaries of the parameter. And so we might decide to have a very unspecific prior because we don't know much. We put a prior, we say any learning rate in reinforcement learning might go. So on a log-out scale, we're going to model the prior in terms of a normal distribution with a mean of 0 and a standard deviation of 5, because we really know nothing, right? It's the first time we're playing with reinforcement learning. We want to see how it works. We want to put something that's really flat. And so we plot the prior, and we can see this nice normal distribution, which should be all fine. Except, right, we might want to check what does that do on the actual scale of the parameter, which is 0 to 1. So what we do is we feed that distribution through an inverse logit, right? And this is what we get, right? So we get that a prior that we thought would be pretty uninformative, it would be pretty flat, instead is very certain that the learning rate is either 0 or 1. That's where, when we work with these nonlinear scales, it's very crucial to visualize in all the scales involved, right? But most specifically in the actual scale of the parameter. Second caution points when we think about priors is that priors in any model that is interesting enough that you're actually spending time with it combine with each other. Meaning these parameters are never playing a role alone in the model. An example that predates something that we'll deal with later, multi-level model, is we have a population level prior, right? On average, bunch of participants will have as a prior for their learning rate, a sensible prior, a normal distribution with a mean of 0 and a standard deviation of 1, which when inverse logitted sort of gives us a nice smooth distribution that only slightly discounts 0 and 1s, and all the other learning rates are pretty possible. And then we say that individual participants can vary from that distribution, right? And again, we have little idea on how these participants will differ. We've experienced that some people seem to play at random and they learn nothing, and some people are really keen in learning. Basically, they're doing a win, shift, lose, win, stay, lose, shift. So we add a broad parameter for a broad prior for the parameter of individual variability, the standard deviation of that population mean. And so we're going to visualize in blue the population prior, and in red, the combined prior for individuals that stems from these mean and these standard deviation. Right, and we see that the population prior is very sensible, but again, it's gonna predict, or it's gonna expect that the participants either learn nothing or learn everything. Does that make sense? Which is why we need to be very careful about priors. They combine, they're a mess. And it's clear why we get these concentration of density at the boundaries, right? Because any value below -3 on a log scale is basically 0. And there is a lot of combined mass below -3, which combines to be bigger than the center here at 0. Given that these priors combine in complex ways, and now they are very similar, right? So it's the prior for learning rate at the population level, mean and standard deviation. But a reinforcement learning model also has a prior for the inverse temperature. Right? How does that combine with the prior for learning rate in constraining the model? Right? That's not something that we can very easily visualize in this way. And that's why what we can do is we can actually get the model to run predictions from all the priors at once and create what we call a prior predictive check. So that we can see the combined effects of all of our priors on the behavior that we're trying to model. So what do we need? We need, for convenience, to actually make sure that the model, as it's running, it saves the priors. So we don't need to generate them post-hoc and potentially make mistakes. And we need to generate and save predictions from a model that has the same shape as the full model that will fit on the data, the same likelihood function, but that will not look at the data. How does that work? Well, remember the Queen Mobile, right? The queen mobile is walking through the posterior space in our example and checking where the probability of the data given the current parameter values and of the parameter values given the prior gets better and better. And following that kind of slope and taking some momentum and hopping over hills and stuff like that, we can actually do the very same operation, but just looking at the probability of the parameter value given the prior. And run the full model. While we're at that, I'm going to anticipate a step because it's going to be exactly the same code. We can also generate and save the predictions from the fitted model within the stand code, within the stand model. So that we have, before the model has seen the data, what does it expect about its participants, about the behavior that it's trying to describe, and after it has seen the data, how have these predictions changed? And how do they relate to the empirical data? So where would we generate and save all of these variables? There is a chunk of the stand model. Yes?
I think it's called generated quantities.
Yes. Generated quantities is a special chunk in the stand model that runs after the model has been fitted. And that is a very good place to generate whatever convenient variables you'll need for visualizing and diagnosing the model, because it's compiled to C++, and therefore it can run very quickly, and it's been optimized to save the data in a meaningful format. Right. So that's this one, right? Good. How do we save the priors? We have the generated quantities, right? And then we can define, because remember, in stand, we always need to define all the variables that we deal with before we can do anything with them. We can define a theta prior, right? Which is going to be, so in this case, it's a rate, right? Could be learning rate. It's a real number. It can have any value between 0 and 1, and it has a boundary at 0 and a boundary at 1. Since we're anticipating some steps, while we're at that, we do the same for theta posterior. Then after we define these new variables, what we do is we generate them. We have that theta prior is equal to the inverse logit of a normal distribution with a mean of 0 and a standard deviation of 1. And I'm using a new function that you haven't seen before, which is RNG, which is random number generator, which basically takes as many samples as you have in your posterior, right? So if you ran 2 chains with 1,000 iterations of warm-up each and 2,000 iterations after warm-up each, you have 4,000 samples, right? And so here it's going to extract 4,000 values from this distribution, pass them through the inverse logit, and save it in theta prior. For theta posterior, right, given that we like to work in logit scales, as we've done last week, right? It takes the posterior that has been estimated by the model above in the parameters, it passes through the inverse logit, and it saves it as theta posterior. Right? So we don't need to do transformation post hoc, where we might make more mistakes on the fly. Good. Now we also want to run predictions. So we need to save two new variables. One is prior predictions, and the other is posterior predictions. The outcome measure, right, is the number of times that a participant or a simulated agent has chosen right out of the number of trials. So we have that it's an integer. The lower is 0, right? It cannot go negative. And the upper is n, where n is the number of trials. The same is for posterior predictions. For simplicity, at this stage, I'm only considering like the random bias agent, which means that posterior and prior predictions are not contingent on the stimuli that the agent is receiving. Right? If we were playing with a probabilistic Wins-Taylor shift model, for instance, right, we might want to also generate posterior predictions that are specific to certain conditions, right? So the propensity, so the number of times that the participant stays after winning out of all the trials in which this happens. The propensity of shifting after blah, blah, blah. It could also be depending, right? If we implemented a bias where the participant could also have a propensity to pick right because they're right-handed no matter what, right? We might want to see the propensity to stay when you win it is right, the propensity to stay when you win it's left, right? So the posterior predictions are really bound by where we want, so by the kind of behaviors that we want to assess in the model, right? With a random bias, it's easy. How many times it picks right or left. As we make more complex models, it's smart to actually also do predictions that are more targeted at the key behaviors of the model. Does that make sense? Because this is really you making sure that the model behaves as you think that it's behaving. Yes.
I think maybe you also specify the prior parameters of model block, right? You
Yes.
also specified the prior for data in that block before.
So yes, this follows on the slides from.
Predictions make sense, but like specifying the data prior again.
Okay, yeah. So what happens is, you're right. Theta in this random bias agent is specified twice. Right? Once in the model block, well, actually 3 times. It's specified in the parameter block as a variable, as a parameter. It's specified in the model block in the sense that we attribute a prior to it. And then we run the likelihood function based on theta, right? And then it's specified again in the generated quantities, right? So what's going on there? As in the model, we specify a prior on theta. This prior is not systematically sampled, right? That's where the target plus equal thing comes in. What happens is that your Queen mobile is looking at what happens at theta equal 0.6, right? And it says, given theta 0.6, what's the probability of generating the data that we're observing? But also, given the prior, what is the probability of 0.6? It's not sampling 1,000,000 times from the prior, but it's simply saying, given the shape of the prior, the analytical shape of the prior, what is the probability of this specific thing? And that's the old thing that it does. So there might be regions of the prior which are never explored because the data is really leading us in a different direction. And given that what we care about is the targets plus equal, that is the combination of the prior and the likelihood, we don't save those two separately. Right? The model is saving the posterior sample that combines both of them. So if we want to have the theta prior or whatever parameter prior ready for visualization, we need to tell the model somewhere to sample it and save it. That's where we're doing this, right? Because we might not need entire regions of the priors if the model is not going there. Yes.
But it's true that you could just as well, because it would be so, but you could just as well generate prior distribution in R.
Yes, you
It's
could.
completely unrelated to what happened before.
Yes, exactly. Yeah. And this is just convenient, right? You have all your variables in the same place, right? And if you're using parameters to define the priors, let's say prior theta mean, prior theta SD, it uses the same parameter in both the model and the generated quantities, and it gets fed through the data to that. So if you're iterating through very many different priors, right, everything gets automatically generated and saved. But you could do that in R, right? That's up to you. This is just more elegant. Does that make sense? Good. Then so we created also these predictions, and then we also generate these predictions. How do we generate? Well, here it's easy. Sometimes it's a bit more complex. So basically we go to the model, we look at the likelihood function, and instead of having a binomial LPMF log probability mass function, we use the RNG, right? Random number generation. Same likelihood function with the same parameters, random number generators. We fit to one, the theta prior, to other, the theta posterior, and we save the outcomes here. Now, if you remember from last time, there is a subtle difference here. In the model, we use the Bernoulli, which is a trial of 1. And here we're using a binomial, which is a trial of n. Why are we doing this? Yes? It's faster and it's more efficient because we don't care about the 0 and 1s, right? We care about how many 1s out of the trials. So since we need to save, let's say, 4,000 posterior predictions, using the binomial and a trial of n, we get 4,000 values. If we ran these at the Bernoulli level, what we would have would be the number of trials times 4,000 0 and 1s, which we could summarize at a later stage. But again, I just want to showcase that this is very flexible. It depends on what you want to do, right? The posterior predictions are not one thing, but they are a way of testing the predictions that are most relevant to the model that you're building. For a random bias, the actual sequence of 0 and 1s is meaningless. If it was a Winns-Taylor shift, the actual sequence or the way it responds to specific situation is actually pretty meaningful. Does that make sense? Good. Then we can draw the prior predictions, right? We have 0 to 120, that's the x-axis. And on the y-axis, we have how frequent that number of right choices is. Right, and you can see it's pretty symmetric. Right? There is a pretty straightforward one-on-one mapping between the rate, in this case, and the number of predicted right choices. And you can see that the most frequent are the central ones between, I don't know, 20 and 100, and the extremes get discounted, as we would expect from the rate prior, the theta prior that we defined. Does that make sense? If we had persisted in our bad idea of a very broad prior, right, just to show you that that happens here as well, right? What we get is, again, that the model is quite certain that the participant will either play mostly 0 or mostly 1. Good. What about the posterior space? Oh, sorry. No, actually. This is what happens for priors, right? As we define priors, we visualize them, we make sure we pay attention to the scale of the parameter and to how the priors combine. In many cases, the easiest way to check how the priors combine is with prior predictive checks. Since here, the numbers are pretty much bound between 0 and 120, the scale is in place. If we were modeling something else, let's say height as a height of people as a function of whatever, and we saw that the prior distribution, the prior predictive checks, sorry, has substantial probability density at 1 kilometer, right? Something is wrong with our model, with our priors at least. We might want to shrink them. Now we've done this exercise, we're satisfied with these predictions. Does that mean that we're safe with priors? No, it's only the first step, right? We want now to go and fit the model and see which impact the priors have on the actual inference from the data. So we fit our model, and now the model is exploring the posterior space. Lots of things can go wrong here before we even get to check whether our priors have had an impact. So what could happen is that we have a model runs, often it runs for a very long time. Sometimes we're lucky, it just fails immediately and tells us. And we have something that's called divergences, or I can't remember what it stands for, but it's something about energy, BFMI warnings, which are two warnings that belong to the same class. What the model is telling you now with divergences, and we'll see a concrete example when we'll do multi-level models, is that you've broken the physics, you've broken the Quinn mobile. You've broken the physics of the simulation. If you remember, what happens is that the model is trying to figure out how the sampler should explore the posterior space. It's learning how big steps it should do before checking the log posterior probability and how many of these steps it should do. And it's optimizing it to explore properly the space. But sometimes the space is very unhomogeneous, right? Heterogeneous. So there are, let's say that lots of the people of Denmark move to skiing, right? It's the summer. Everybody goes to this very narrow place. And the Queen Mobile is trying to explore the space of Denmark to spend a proportional time in areas according to how populated they are. More times in areas that are highly populated, less time in areas that are less densely populated. But as it goes up to skiing, right, it makes steps of, let's say, 600 meters. And it arrives in skiing, it sees there's a lot of population around it. In this direction, in front of me, there's more population, so it should move in that direction. and it should make a step of 600 meters. It expects that the population density will increase accordingly to what it has seen around it. Makes 600 meters and suddenly it's in the water. There's nobody around it. So its prediction gets broken. And this is a divergence. In the metaphor of space, what you have is that as a particle moves in space, it acquires a certain momentum. It looks at any given point in time, it has a specific amount of kinetic energy, how fast it's moving, and potential energy, right? How high it is, how much it can go. If at the next step that we're sampling in a discrete way, because we're a computer in this case, and the computer is not a continuous machine, right? If at the next step, the trade-off, the balance between kinetic and potential energy is not preserved, we've broken the assumptions of the simulation. We've broken the physics. And the model is telling us, watch out, right? Even if we tried really hard to optimize your Queen Mobile to explore Denmark, your sampler to explore the posterior space, there are regions of the posterior space that cannot be explored nicely. There's something weird that goes on. So beware, your inference will not hold for the whole of the posterior space because there is this weird region. We'll go more in the details of this when we do multi-level modeling because it's easier with an example. The second, I messed up the order of things, but this is an example that we'll see, right? We have the population level mean on the x-axis, that's the plot on the right for the people of the Zoom. The y-axis is, let's say, the population standard deviation, I can't remember. We have that most of the space, the part that is in above -4 on the y-axis has a certain spread in space. But as we go lower on the y-axis, there is a funnel. I don't know how you say that in Danish, but it's the thing that you use for pouring oil in a bottle or something. Right? And if you optimize your steps to explore the higher part of the plot, right, you will have steps that are, I don't know, 0.05 or even 0.01. But as you go down here, you're just going to be pinballing, right? It's very easy for you to do a step and suddenly be outside of the funnel and break the assumptions of the trade-off between kinetic and potential energy, right? Between what you expect to be seeing and what you actually see around you. And that is something that we deal with, either changing the priors, making the hyperparameter tuning, that is the learning of the steps, different, but that really never works. What we need to do is a fun thing called reparameterization, that is changing the geometrical, the topology of the posterior space, changing the math that generates your model. Sounds fancy? You've done it already. When you standardized your predictors, when running regressions, you made transformations on the parameter space. That has been a kind of reparameterization. We'll see how we can extend that kind of reasoning to the parameters and not just to the variables, to the predictors. The second thing that might go wrong, that you need to check, is that you might have, right? We said these processes are stochastic. They contain a random component. You start at random and then you move around in a slightly stochastic fashion, right? Which means that if you start two different processes, they might end in different places, right? If suddenly there is a succession and there's two quarreling queens in Denmark with their queen mobiles, and they both want to cover the populace to gather support, right, for their civil war, which will be fought at MKP, right, with the two queens singing. Then what happens is that if their algorithm to sample the population space, if our sampler has a good setup, they will cover the same areas, the same roughly amount of times. But if they have different algorithms which are not as well reflecting the underlying population density of Denmark, they might be exploring different areas differently from each other. And that's a sign that we're not sampling the population density properly. So here you see some representations of the chain. So we've seen that you can run more than one chain in your sampler. And we see the iterations on the x-axis. We see the value that is sampled on the y-axis. And we see that different chains are exploring the space very differently. Not only that, but that their steps are highly correlated. That is, where you are at iteration n is highly predictive of where you are at iteration n+1. Meaning that the exploration of the space is highly dependent on the initial conditions, on where it is. And that's bad. Because we want the space to determine how we explore it. The topology of the space. On the lower part of this plot, what we see instead are chains that in technical terms are mixing well. In less technical terms, or more technical terms if you want, look like a hairy caterpillar, where each chain is sort of swinging widely on the y-axis, and really it's hard to pinpoint any difference between the chains. This tells us that the queen mobiles are exploring Denmark in a way that does justice to its population. Right? They're good queens. Maybe they could rule together. I can't bring myself to do the king mobile. I think it's queen mobile is so much better. Yes.
Doing a bit of time grasping how where you go in the next sample, not being conditioned by where you are makes sense. Compared to like if you're going towards Copenhagen, there's a very dense population. That depends on where you want to keep going that direction.
But you don't want to be trapped there. That's the big problem of Denmark, right? That's why the queen has a castle here. Right? You don't want to be trapped in a specific place. Am I bringing the metaphor too far? No, but really, so the idea is that's the basic idea behind the Hamiltonian Monte Carlo is that you always have a momentum. So even if you're revisiting the high density places many times, as you should, you don't get trapped by that. So if there are,
So it's about coming back a lot of times, not about
keeping there.
Not about being there.
Yes, it's about it keeps bringing you back. Right? But you also want to be in Odense and Aarhus and Aalborg and all the other places, right? Because those are regions where the probability of the posterior probability of the parameter values are non-trivial. So where the population density is non-trivial. If you're trying to gather support in your subjects in Denmark, you want to also take all of those areas, and every now and then take to Udkantsdanmark, right? To the outer Denmark. Yes.
Just try to completely destroy your metaphor here.
Yes.
So if you had, if you had a distribution that was like the population from like highly, a bimodal or like multimodal, you can call it, that would be extremely difficult to sample, right? With these like
It
Because
is,
there's so much empty space, like when you have these clusters.
it is difficult, but Hamiltonian Monte Carlo so far is the best sampler of doing
Yeah.
that. It's having a hard time in doing that, but it does it better than a lot of other samplers because of the momentum component.
Yeah.
And then what you would want is many chains, right? To make sure that at least one of them will end in the different modes. And that will tell you something about the chains will not converge, but it will tell you something about the different region in which you might.
Yeah. And
Yes.
also, so in that case, you would have, many fuzzy caterpillars that are sort of stacked on top of each other. If the parameter is the x-axis of Denmark, for example, they would not necessarily explore the same space. So that would make the caterpillar a bad representation of whether or not this sampling is sufficiently well spread.
Well, you would have more than one caterpillar, right? Instead of having these divergent lines, you would have divergent caterpillars.
Yeah.
And that would be telling of the diagnosis.
So I think my point is that in the case where you have bimodal distribution, for example, that is not necessarily bad that you have two caterpillars. That they're not exploring the same space, but they might be exploring different.
To bring back the Queen Mobile metaphor, Denmark has, let's call them what they are, colonies. Greenland, the Faroe Islands, Bornholm, right? This is not recorded, right? The Queen Mobile cannot sample Denmark, the Faroe Islands, Greenland, and Bornholm, and in the old times, the Virgin Islands, right? Without starting in those places, right? So that the metaphor keeps on working. You need a really good momentum to run your car and then out. This works out, right?
But the sampling is more like, she doesn't know she has Greenland unless you randomly start her there.
Exactly. And that's where the problem of multimodality is, right? That when you have problem that has this multimodal, and multimodal means with many modes, structures, you might not know that because the sampler has to start there to show you that it's a problem. Right. Yes. But again, now I'm giving you the overview. We'll see these things in the details of examples. What's the time?
8 minutes past.
Okay, should we take a break? Good. Yes. Okay, we should getting back into the Queen Mobile. So the last thing that I want to discuss briefly before we get into more stand code and more assessment is there is another important indication of how the sampling has gone in the effective sample size. What does that mean? It means that, let's say that you ran the model we discussed before, you're expecting to have 4,000 posterior samples. But if the posterior samples are as in the chains in the upper yellow plot, what you're seeing is that one iteration and the next iteration are not giving you independent information. Which means that if your steps are highly correlated, you're not getting as much information from the posterior region as you think you are from having 4,000 samples. So what STAN does is it gives you an estimate of effective sample size that is, if, let's say, the autocorrelation, the correlation between T and T+1 fades away when you have t plus 2, right? It will only discount your number of samples a bit. If the autocorrelation persists, it will discount it a lot. So sometimes you might have 4,000 posterior samples, but 1 effective sample size, meaning that it just all the chains get stuck somewhere, right? Or 20. What are the practical implications of the effective sample size? The practical implication is that, remember, we're trying to draw a distribution. If we have 20 effective samples, how good a picture of the distribution are we getting? Right? Not very good. Right? It's the same as if you only test 20 participants and you expect your population to be very heterogeneous, let's say patients with schizophrenia. Right? 20 is not going to be very representative of the distribution. Could it be representative of the mean? Well, it depends a bit on your problem. And that's why Stan gives you 2 different effective sample sizes. One is for the bulk, the mode of the distribution, and the other is for the tails. If you're only interested in the bulk of the distribution, right, then this is how well the chains are exploring the bulk of the distribution, how reliable an estimate of the mode you're getting. The second value is how reliable an estimate of the tails you're getting. Sometimes getting a good estimate of the tails is not that important. Sometimes it's quite important. It really depends on your problem. And that's why you get 2 different ones. And as you can imagine, exploring the tails is much harder than exploring the bulk, right? Because you end up there much less frequently. Yes?
Can a sample be both in the bulk and the tail? Or are they summing to? If all our samples are affected, with the 2 sum to the number of samples?
No. So what happens, this is not the number of times that the sampler ends in the bulk and the number of times that the sampler ends in the tail, is an estimate of how correlated the sampling is when you're out in the tails and how correlated the sampling is when you're in the bulk. Right. Paradoxically, I haven't really seen it happen. But paradoxically, you might have that it's less correlated in the tails, and therefore you have a higher effective sample size in the tails. I haven't seen it. Technically, it is possible, I think. What is a good effective sample size? Again, it depends on your needs of precision, but there are rules of thumb to start with. For instance, saying that if you want a good estimate of a mode, and you have fewer than 200 effective sample size, that's going to be pretty crappy, right? If you have good estimates of the tails, right, then you're going to be wanting at least 1,000 sample size because the tails might be long. You don't know, right? And so you want really the sampler to be able to explore the tail space. Some people would say 200 and 200. Tails are tricky, right? If those are important for your model, make sure that you have a lot of effective sample sizes. We've seen 3 different ways of seeing whether the posterior space is explored in a decent way. Is one better than the other? No. If one works, can you be happy? No, you need everything to work because they're diagnosing different ways in which the process can go wrong. The good thing with Stan is that it fails very often and catastrophically if things are wrong, right? It's going to tell you if anything is not working, which is better than getting a solution and the solution being wrong. Good. So what you do if there are issues, the first thing you need to do is double check your data. I mentioned before, right, that I was trying to look at a reinforcement learning model. And when I was loading the data, for whatever silly reason, I have no idea why, but the trial order got shuffled. And the model kept giving me wrong or divergences. You want to double check your code. Sometimes you make silly mistakes in your code. You want to play with your priors, right? Sometimes you have too broad priors. You end up in regions of the space that are not very likely, but you get trapped there. You might be cutting regions of the space that are important and the sampler keeps bumping against the boundary. So you need to play with the priors and see how it's going. You might adjust the fine-tuning parameters that we discussed last week, the depth delta and max tree depth. That is how the model is learning how to adjust the step size and the length and the number of the steps in the sampling of the posterior space. If everything seems okay, but you have a low effective sample size, you can increase the iterations. If you're really desperate, but it's never going to work, you could increase the warm-up so the model has more time to learn. I always do that. It never works. The really thing, well, priors, you might be lucky. But really, the only very effective way of tackling serious divergence issues or problems with the chains is reparametrizing. So rethinking the mathematical form of your model. We'll see concrete examples when we do multi-level modeling because it's easier there. And there's a very good handbook page, which I put in the slide because it helps you going through these different error messages that you might be getting. Okay, now that we ensure that the model is exploring the posterior space in a decent way, right? We might want to see what is the model learning from the data and which kind of prediction it's making after having seen the data. So I really, really like prior posterior update checks, which are nothing but taking the prior, plotting it, taking the posterior, plotting it. Here we even have a true because it's from a simulation. Plot that as well. And then we observe whether the posterior is within the region of parameter values that's defined by the prior. Here, our prior covers basically all the possible values in the parameter, so it's hard not to capture where the posterior is going. But if the posterior was really stubbornly at 1, right, we might have discounted the posterior a bit, right? We want to know whether the posterior has become more certain than the prior. Because that means that by looking at the data, the model has learned something, has become more confident, which is how concentrated the probability density here. Here you can see the prior is very diffuse, the posterior is very concentrated. Is there a test to know whether the posterior has learned enough? My gut answer is no, think. Right. There is no dichotomous test that tells you whether it's enough or not. You need to reason carefully in your specific context. There have been, however, rules that have been suggested, which I feel obliged to let you know are there. For instance, Gelman says that Gelman is one of the developers or the people who developed all the conceptual framework behind SAN. But if the standard deviation of however you measure the variance of your posterior is more than a 10th of the variance of your prior, then your model has not learned. Where does a 10th come from? I have no idea. It's a rule of thumb. I don't like the dichotomous things, but it might be a useful reference. Is the posterior capturing the truth? Please?
Really. Well, it certainly has to learn something,
Mm-hmm.
but the mode of the posterior is too low.
Okay, yes. So rephrasing, we have a truth that's 0.8. We see the mode of the posterior is 0.75, which is lower than 0.8, which might bring us to say the posterior is not capturing the truth. The counter argument is the posterior is a distribution, right? The truth is falling within a non-trivial portion of the posterior. But yes, something is happening. Why do you think that the posterior is not exactly capturing the truth? Yes?
Maybe the priors having too much of an effect.
Yes, the prior is being skeptical, right? It's saying discount exactly 0 and exactly 1 and in values that are close to 0 and 1. And therefore, it pulls all estimates a bit towards the middle. Whether this is a bad or a good thing, again, depends on your problem, right? We might not want to be too confident if we have a limited amount of data, right? So pulling towards a middle state of uncertainty might be a good thing, which is only overcome once we collect enough data. Or it might be that, oh, we think it's a bit too strict because we have no reason to have the mean in the middle, right? The pool towards 0.5. So we might want to go back and try to make it flatter without having the peaks at 0 and 1s. Does that make sense? Good. Now we're looking at one example, right? One set of parameter values for the prior and one truth. We will get to look at how we can systematically test a full range of parameter values for the priors and for the truth, so we can have a better picture of what are the priors doing to our influence and what can our model learn. Does that make sense? Good. But quickly, are the predictions right? We'll plot the posterior predictions that we designed before. We see that now it's shrunk from 0 to 120 to 70 to 110, right? That mirrors the shrinking of the posterior from the prior. The red triangle is the truth. We can also look at how the predictions change from prior to posterior predictions. Again, it mirrors a bit what we've seen in the prior and posterior of the theta parameter, but once we have more complex models, this is going to be more important, right? The model has learned, has shrunk its predictions in the right direction, right? It has shrunk them centered roughly on the true value. Good. That was the easy one. Let's look at a more complex model, right? A model with memory. A model that conditions theta, the propensity to pick right, on a bias that is a propensity to pick right or left no matter what. And how many times you've seen right before weighted by a beta parameter, right? Where your memory might count more or less according to, well, maybe we want to estimate how much the memory is counting for the agent. So we've seen these before. We generated some data, right? We subset random agent, which has no noise because we just want to see what happens, and a rate of 0.8. And then we create a memory agent with no bias and a very high weight for memory to play against it. We've went through that, so I'm not going to do the full line by line. Here is the memory agent function. And here we make it play on a trial by trial base against the random agent. We create the data for Stan. There's a number of trials. There's the choices that the memory agent has made. And there's the choices that the random bias agent has taken. We create the model. Right. In the data, there's exactly the 3 kind of data that we just put in the list. We define the parameters accepted by the model. Now the parameters that we need to estimate is not theta anymore, but it's the bias and the beta for memory. They don't have boundaries. Why? Because now we're not estimating theta anymore, which is bound between 0 and 1, but we're putting a full linear model into that. The full linear model, in order to then fit into the 0-1 space, is passed through inverse logic, which means that the bias and the beta are on log odds. And log odds can go from -infinite to +infinite. A negative bias means a propensity to choose left, no matter what. The more negative, the more extreme. If it's positive, it's the propensity to choose right. The more positive, the more extreme. The beta is in log odds again, right? If it's positive, it says follow the propensity to choose right. If the other person is more likely to choose right as well to match, to guess where they've hidden the penny. If it were negative, it might be an agent that's trying to do the opposite. If the other person tends to choose right, go left, which means that this model is able to capture the behavior both of the matcher and of the hider. We could artificially constrain it to be positive, right? If we think we would just put a lower limit, that would be easy. We're not doing it here. We do transform parameters, so it keeps memory of what the other is doing on a trial by trial basis. We have the model where we have 2 priors, 1 for bias, 1 for beta. I'm putting some values there based on experience. You might have picked other values. They help me, those specific values, make a pedagogical point, because what we're going to do is to check whether they're good. Right? We don't pull them out of our R's and just use them, but we actually think a bit, but don't overthink. We can put some values and see how they work and understand the model better. Right? 0 to 0.3 for bias, because we don't expect a huge bias, people just going right, or left. And then we don't really know much about memory. Let's put something broader, 0.5. Then we loop on a trial by trial base, a Bernoulli logic that tries to predict the choice of right or left for that trial, given the bias plus beta times how many times, or the rate that the other has been using to pick right, put through a logic, because we're in a log odds space. And then we have generated quantity. Bias prior, beta prior. And here we do predictions, as I was telling you before. Right? What happens if the agent has seen equal propensity of the opponent to choose left and right? Call it 5 as 0.5. What happens if the agent has seen a propensity of 0.7? What happens if the agent has seen a propensity of 0.9? Because I'm trying to understand the model, right? Given the rate, the bias, and the beta that is inferred for the agent, how would it behave in these very specific conditions? Normal random number generator for the bias prior, And here I made a mistake. I should have updated it to 0.3. That's on me. Normal random number generator for the beta prior. That's where I say use variables instead of numbers, because then you forget. I forget to update. And then for the prior and posterior predictions, we have a binomial random number generator with the number of trials. And then we have the linear model bias, in this case, prior plus beta prior, but we fix the memory. We say what happens at 0.5. And we do the same for 0.7 and 0.9. Since in this case, the memory is symmetric, we don't really need to do also 0.3 and 0.1 if we have 0.7 and 0.9. Write the stand file, we load it, compile it, we fit it, we generate the summary. And then we can do quality checks. We look at the, I mixed up the colors, darn. So we have in blue is the prior. Is it? Yes, at least here. No, there's something wrong. I knew I should have rerun the code last night. The red is the prior. Okay, the red, no, you're right. The red is the prior. Sorry, I haven't messed up the colors. The red is the prior. The blue is the posterior. The red is the prior, the blue is the posterior. The dark vertical line is what we actually generated in the simulated data. What you see here is the model learning. Remember, the red is the prior, the blue is the posterior. So the model doesn't seem to be learning a lot, especially in the beta for memory. It gets only a tiny bit more confident, but really the shape is more or less the same. Right? The range of parameters covered is only slightly shifted towards the truth. The model is not learning. For the bias, it's even worse. Right? The model is trying to move away from the prior, but the prior is clearly keeping it constrained. It's very certain. And even worse, the posterior is moving away from the truth. That's where I was getting confused, right? Because this should not happen. Something went really wrong with the model. We didn't get any divergence. The chain seemed okay, right? What has gone on here? Yes.
So, I mean, my interpretation would be that depending on how exactly the model is set up, it seems like it's easier to explain the observed data just by saying, well, the bias was high, instead of saying there was memory in the process. So it seems like there's some sort of trade-off between the prior estimation process, which makes it impossible to distinguish.
Yes. Given the so there's two aspects. One is what you're saying, and I'm gonna repeat it for the people of the Zoom, but basically is that given that the random agent that they're playing against, the agent is playing against, is playing right more often than left, whether this agent, the memory agent, is following its memory or simply having a bias, hard to establish, right? The second problem is that we clearly have two narrow priors, right? The model is having a hard time learning from the data because the priors are very constraining. These two problems are conceptually orthogonal, but in practice, they bleed into each other. So we can do something with the first problem also by fixing the priors. Does that make sense? Okay, we can look at predictions, right? And that really confirms that the model is not learning a lot. Well, it's learning something, but, oh, actually, sorry. Yes. Right, so we were seeing here that the model doesn't seem to be learning the right stuff, but we see what Ingrid was saying, that in the prior predictive checks, right, the predictions for different rates of observed right don't really vary that much. They're pretty much overlapping. In the posterior, they're still uncertain, but they're mapped nicely where when we observe a lower rate in the agent, we get predictions that tend to be less extreme towards right. As the rate in the random agent increase, then we have an increase in predicted choices of right. So what we can do is to say, can we solve the problem by changing the priors? And this is going to be the last thing of today, right? How much is our estimate affected by prior values? We define a range of reasonable values and iterate over those values. The prior mean and the prior standard deviation. And then we let Stan know that those values are part of the data so that we don't need to recompile the model every time and we don't make the silly errors that I made. I think I've left this example only on the previous model, estimating the random bias. So the two priors are the mean theta and the standard deviation of the theta. But what we do is we add two additional elements to the data in Stan, a real, which is the prior mean, and a real with a bound at 0, that's the prior standard deviation, because standard deviations cannot be negative. We replace in the LPDF that generates the prior, the numbers with those values. Then we create the sequence of prior means and prior standard deviations, sequence from -3 to 3 for the prior mean in steps of 0.5, from 0.1 to 1 in steps of 0.1 for the standard deviation. We create the full grid, the full combinations of these parameters. We create a table with these values, simply a data frame. And we compile the model. Then we select a random bias agent against which we can make the agent play. And then we create a function, which given a value for the prior mean and a value for the prior standard deviation, it creates the data. It samples the model. It extracts the posterior samples from the model, and then it saves them in a table. The theta prior, the theta posterior, the prior predictions, the posterior prediction, the prior mean, the prior standard deviation. And then it returns that table, which means we can fit it to a parallelizing function, which is the future P map. Are you familiar with this parallelization stuff? But so there is a package which made parallelization very easy. It's called FURR, F-U-R-R-R, where people in the tidyverse are funny, right? Map is it maps a series of values onto a function. Future, it means it's parallelized. And DFR, it means it spits out a data frame. I can't remember if it spits out or reads a data frame, I think. Then we have our priors, which are the parameters that we're changing, right? The people that we created in the previous slide. Right, the priors with all the combinations. We feed it to that function, cindy and fit. And then we let it run. And it parallelizes that across the cores in our computer. So it gets much faster. And then we can plot the outcome where prior mean is plotted against the theta posterior. The impact of the mean of the prior that we've chosen on the estimated theta. And then we split it by panel according to the standard deviation of the prior. And we can see here on the x-axis, there is the prior mean. On the y-axis, there is the this is the posterior estimates, sorry. And we see that with low standard deviation, meaning with very high confidence, the prior mean is very determining the posterior estimate. As we decrease the certainty, increase the standard deviation, the influence of the prior mean disappears. Right? And then here we can plot it the opposite way. So if we vary the prior standard deviation, how does the theta posterior changes as a function independent of the prior mean? And again, we see what we were seeing there, that basically independently of the prior mean, what's really having a big impact is how confident the prior is. And we can see that independently of the prior mean, really we can figure out a region of stability where changing the standard deviation doesn't affect the results anymore. If that's what you're going for, right? If you want to make sure that your priors are not affecting unduly the estimate. Yes?
What's the value of your
So on the x-axis is the standard deviation, and the facet is the prior mean. Right. And really what this is telling us is that what counts as the standard deviation, right? Because in each of these plots, unless you have a prior mean that's relatively close to what you're trying to estimate, high confidence in the prior will lead you astray. So if you have a prior standard deviation, which is above, I don't know, 0.5 to be sure, you're in a region of stability where increasing it is not going to change your results. I see a question there.
No, I just need to think.
Yes. So this is the tool, right? Are we sure of our priors? What impact are our priors having? Well, let's simulate. Let's see how much they're impacting our estimate.
So it's, yeah. So this plot is kind of showing the impact of the standard deviation of the prior.
Yeah, so yes, so there's two ways of visualizing exactly the same data. In one, we're faceting by standard deviation, in the other by prior mean.
This one is faceting by standard.
Yes.
Okay.
Yeah.
Can we make any decisions based on this?
Yes.
So do we want to select a standard deviation in the area where it's stable?
It depends on your goals. So for instance, if you're regularizing, meaning if you want the data to work extra hard to persuade you that there is an effect, then you might want to be before the region of stability. You want your prior to be affecting the results, making it extra hard to move away from zero if you want. If your goal is simply estimating and the priors are just a way of making the model work, then you want your prior to be at the beginning of the region of stability, where they're not affecting the inference, but likely they're helping the sampler to get in a good place. Does that make sense?
Yeah, can you repeat the first scenario?
Yes. So in the first scenario, actually, there's many scenarios. So you might be in a scenario where you want your priors to matter. Why so? Well, maybe you ran a previous experiment and that information shouldn't be discounted. Or maybe you want to see how well your results match with a previous meta-analysis. Or maybe you're simply skeptical and you're doing a first study in assessing how much drinking a raw egg before advanced cognitive modeling really helps you getting everything, right? And you want to be slightly skeptical. So even if the raw data would tell you that there is an effect, you might want to have a prior that says, well, we're actually centered at 0 effects, and we're quite confident prior that that will not affect it. And then we want to see what is the posterior estimate of drinking, of the random allocation of half of you drinking a raw egg, right, before class. And in that sense, you don't want to believe the raw estimate, right? You want the evidence from the data to be overwhelming your initial skepticism. So the fact that your prior is affecting the estimate, that's fine, right? Because you want the evidence to really be overwhelming. Does that make sense? Or if you have 10 predictors, we know that if you have 10 predictors, some are going to be very close to a region of significance if you want to speak frequentist terms. So you want your prior to be shrinking them towards 0, so that only those that really have overwhelming evidence have an effect, or are estimated to have an effect. Or are estimated, even we're not doing causal inference here, are estimated to have a relationship with the outcome. Yes.
Is it often that you have the problem that your model doesn't run and you can address that problem by adjusting the priors?
Yes, that happens a lot.
It seems to me that there is a bit of an odds, like there's 2 different uses for adjusting the priors. Something like one is to make it correspond to the previously held beliefs about what you expect, and the other is very practical, will it work? And those are not necessarily aligned, right?
No, and 90% of your prior fiddling is to make the model work. There's very few studies that are using informed priors in meaningful ways, which I think is a pity. If you want to know more about that topic, there is a whole lecture that I gave at a summer school on Bayesian statistics on the impact of priors, which I think was linked in the prepping your brain for on Brightspace. But yes, so that's where people worrying about priors bringing subjectivity for cognitive modelers or serious Bayesian modelers is always a bit ridiculous, because we fiddle with priors not to get results, but just to get the Dan model to run. It's really not about the results. Yes. What's the time now? Okay. This is just running it at the outcome scale. And basically, parameter recovery is nothing else than what we've done before, but we change the true parameter values in the simulation. So there is a function which is exactly like before, but for instance, you could have the rate level of the random agent and the noise level. We do the same table, the same future P map. And then we look at how a model, in this case with a fixed set of priors, because things explode, recovers the rate mean of the random bias agent with 0 noise, 0.1 noise, 0.2 noise, 0.3 noise, 0.4 noise, 0.5 noise. Right? You can see that it preserves the rank, but the estimates become both more uncertain and less clearly ranked the more we increase the noise. Make sense? Right. And then we can discuss next week whether we can quantify this, right? Or whether it's just a visual inspection. Good.